I guess we're greater than 50%. I guess that's a quorum. I think there's 11 students out of 20. Whatever everyone wants. Or people just, now that I have all the lectures online, they just look it online.
Well, we didn't record.
For the last one I know, but I put the previous one up,
Yeah.
the noon. So, oh, so you do look at them. Okay, I should start posting the notes too, so I haven't done that yet. Anyways, I'm sure everyone knows there's a storm headed our way again. I do not know the fate of Wednesday, but we'll find out on Wednesday. They've canceled all the extracurricular activities on Tuesday. So at least the ones like the clubs. So you can look at work. If you look at a UH email, at least I got alerts from it. I don't know if you guys get the alerts.
Yeah.
So only a category 1. Well, it's not supposed to be a tropical storm. But a little time it hits. Anyways, does anybody have any questions or anything before we start? I'm gonna get through. Okay, this is where we left off. We're talking about hydrogen. But we're going to convert 1 gallon of water into grams of hydrogen. So the way we do this, so dimensional analysis we're doing, start off with 1 gallon of water. And so just with dimensional analysis, start with what you're given on the left and then fill in the units as you go to the right. And so a gallon of water is 3.78 liters. I just know that because I knew that. Because if you look at a gallon of milk, it says 3.7 or 3.8 liters. And water, a liter of water weighs a kilogram. This one here, I'll be consistent with the units. You can put a kilogram here. If not, you can put 1,000 milliliters per liter. It's water. Just say water. You don't really have to put the units of water. I mean, milliliters and liters. That's true for no matter what fluid you're using. 1 gram water to 1 milliliter water. That's probably good to label that one. And then still work with moles. So convert to moles. And then you can, the next step here, you can do one of two things. You can say mole hydrogen, 2 mole water, and then 2 grams hydrogen, 2 mole hydrogen. Or you could, if you want, you can put 2 mole H and then 1 gram hydrogen per mole hydrogen. Either one works, however you want to do it. If I remember correctly, the answer is 420, because I just did this. 3.78 times 1,000 divided by 18 times 2. Yep, 420. Okay. This problem, how much hydrogen's in a gallon of water? And put it all in, you get 420 grams of water. That's not even a pound of water. That's or a pound of hydrogen. And a gallon of water, so 3.7 times 2.2. That's about like 8.5 pounds. So that's why is that? Why do you get so little bit of hydrogen? It's because it's so light. Because water is 8/9 oxygen and 1/9 hydrogen. So, but with this problem though, it's just more dimensional analysis than the idea. And I'm trying to get in your mind when you see some in chemistry, like what's it in moles? I give you something. Okay, how many moles is that, and what can I do with those moles? So, questions with this so far? Good question? No. All right, where we should have gotten last class, but a little behind. Empirical formula. So what's an empirical formula? It's the lowest ratio of atoms. So if you look here, C6H6, that's benzene, and C2H2, that's acetylene or ethine is the proper name for it. So these both have the ratio of one carbon to one hydrogen. Excuse me, one carbon and one hydrogen. So the empirical formula for both of these is one carbon and one hydrogen, but there's a bunch of different molecules you can get from this. For instance, benzene and acetylene, and they're both very different molecules. One we use in welding torches, the other one we put in gasoline. So, and it's a liquid. Benzene's a liquid, and it smells pretty strongly. So, one thing to watch out for that. If you look at this problem here, so a compound has 24.5 grams of nitrogen and 70 grams of oxygen. What's the empirical formula? This came back from chemistry when we were trying to figure out what's in this stuff. So we do various things, and one of the easiest ways to figure things out is to burn them. And oxygen for a while was just the missing mass. So compounds that contained oxygen, that was kind of like there's some mass here, we don't know what it is, and that's one of the things that led to the discovery of oxygen, as a matter of fact. But for this one here, how do we solve this problem? So 24.5 grams of nitrogen and 70 grams of oxygen. And now I want you to think of moles. Moles, nitrogen, moles, oxygen. Mole, that's lower, moles. Oh, I'm sorry, moles, jeez, what am I doing? 14 grams nitrogen, moles oxygen, 16 grams oxygen. Okay, where am I getting the 14 and 16 from? If you look at the periodic table, and it's hard to see that all the way in the back, but underneath nitrogen says 14.007, oxygen is 15.999. So it's the numbers in the bottom on the periodic table there. That's where I'm getting that. And you do not have to memorize the periodic table. One will be provided to you. So, and what is this? 24.5 divided by 14. This is 1.75. And then 70 divided by 16. This is 4.375. And you're like, okay, fine. So that means we have nitrogen 1.75, oxygen 4.375. This doesn't work. You can't do that because when you deal with molecules, you have to deal with whole numbers. It's discrete mathematics. So just like with people, I remember I was doing some calculations for a number of people on a line when I was an intern for an engineering company. And I figured out that we need 13.2 people at this spot. It means we need 14 people. So that kind of thing. So you have to work with whole numbers, just like with people. People are whole numbers. Atoms are discrete mathematics, just like people. So what do? We divide both sides by 1.75. Of course, we get 1 here. And then for oxygen, 0.75. And for oxygen, we get 2.5. Can we say nitrogen, oxygen 2.5? No, we can't have a half an oxygen, so what do? We multiply by 2, and we get N2O5, so dinitrogen pentaoxide. And the next question I get is, what do I know what number to multiply things by? If you look here, so if it's 0.5, that means it's a half multiplied by 2. If it's close to 0.33, it's close to a third multiplied by 3. If it's close to 0.25, multiplied by 4 for a quarter. It's 0.5 multiplied by 5 for a fifth. So, with this in mind, ibuprofen is 75.69% carbon, 8.8% hydrogen, and 15.51% oxygen. What is the empirical formula of ibuprofen? And you're like, wait a second, this is percentages. How do I deal with this? Pick a good number a number I would pick is 100. And then because of that, I would get 75.69 grams of carbon, 8.8 grams of hydrogen, and then 15.51 grams of oxygen. And this is mole carbon to 12 grams carbon, mole hydrogen to 0.008. Hydrogen here, it's best to put, I normally use 1, but there's a little bit of truncation error at the end if I don't do this, and then students can get upset. So once you start working on it, is anybody stuck? Anybody lost? Raise your hand if you have no idea what the heck's going on.
Why did you change it back to grams from percent to grams?
Because, so, you have to figure out moles. So from the percent of the elements, you have to get the molar ratios, and you get it by mass, right? So you can convert mass to moles, can't necessarily convert percent to moles. So unless it's a mole percent, but this is a mass percent. So what do you do next? You divide by the lowest. 0.96. For what? It's 3B. B, beta. Boy, I don't know.
Okay, so the first ratio is divide by the lowest.
Yeah, I said a good question. It was if you 9.00596645277, and oh, that's hydrogen. Sorry. And this is 1. This is 1. This is 6.506696982592. I mean, do the truncation, ka-chink. So you would have carbon 6.5. Oh, hydrogen is 5. Hydrogen 9. Oxygen. And so what do you do here? By 2, so carbon 13, H18, O2. And if you wanted to, you can go to the previous part of the lecture and you can see ibuprofen's right there. So you can always cheat. So does anybody have any questions on how to do this? Okay, this is how to balance chemical equations. I know we're going to jump topics yet again. So this here, chemical equation is much like a recipe. So it's almost like making pancakes. So cup of flour, an egg, 3/4 cups of milk, teaspoon of baking powder, mix it together, make pancakes. So depends on how big you want your pancakes. That can make you about 5 of my pancakes. So same idea, 1 part CH4 plus 2 parts oxygen makes 1 part CO2 and 2 parts water. And something to note here, this is balanced, and there's the same number of each type of atom on both sides. So the black atom is carbon, so 1 carbon here, 1 carbon here. The red one is oxygen, 1, 2, 3, 4 oxygens, 1, 2, 3, 4 oxygens. And then the hydrogens, 1, 2, 3, 4 hydrogens here, 1, 2, 3, 4 hydrogens there. And we haven't gotten to the shapes of molecules yet. We will learn more about that when we get to chapters 9 and 10. So, but the way that you balance a chemical equation is you pick an atom and you balance it through. And then remember also they have to be whole numbers. So let me illustrate here. So C4H10, pick an atom. I'm going to pick carbon. So there are 4 carbons here. So then there's 4 carbons there. The next one is hydrogen. There's 10 hydrogens here, so we need 10 hydrogens over here. So I'll multiply by 5 here. So what you cannot do, you can't say, you know what, I'm just going to get rid of this 10 and make it C4H2, and then I'll be done with it. You can't do that, because if you do that, then you change the compound. So can't change the compound. You got to keep the compound, the ratio of those atoms the same. So next thing, you can see that oxygen has to be an even number. There are 2 ways you can do this. You can just balance it and have a fraction and then multiply it by 2, or you can start off by multiplying it by 2. So I'll show you the fractional method first. So there are 8 oxygens here from the CO2, and there are 5 from there. So this is 13 oxygens. So this is 13 halves oxygens. And you can't have a half an oxygen atom. So what you would do is you would multiply everything by 2, and you would get 13, 8, 10, and 2 like that. So 2 ways to do it. Or the other way is you can just start off by multiplying it by 2, since you already know that there's going to be an odd number. and where we were before, multiplying by 2, we were without there. So from this, we have 10 oxygens plus 16. So 8 times 2 for the CO2 is 16. So 10 plus 16 is 26. 26 divided by 2 is 13. So it's whatever way you want to do it. Does anybody have any questions about it? Do you understand my logic? Okay, so let's try this out, and feel free to work in groups. How many waters in the balanced chemical equation? I want to know this number, the number before the H2O in that chemical equation. So if anyone is stuck, please feel free to raise his or her hand. Okay.
Yeah, start. But because of the so start off with 1. Here's 4. There's 4 here, so 4 carbons, 10 hydrogens, 5 phosphorus, 10. Right? But the problem is now there's an odd number. Yeah. That's what we got the 8. Alright. This was a little difficult, so we should go back to this. Should I have all the confusion in the classroom and on the test? you get it. You get it. Well, you don't have the, it wouldn't be 24.
Yeah.
Because, yeah, 13. It would be 24 from that, and you have another 13. It would be 24 plus 13. 37. 37 halves. So that's 24. So 12 times 2 is 24. But, okay, but 24, actually that's 48 oxygens. So here you have 24 oxygens plus 13, that's 37. So it'd be right here, 37 halves. Well, this is, you gotta multiply it. Do you see what 37 is?
Yeah. What if I almost didn't know to do with it?
Yeah. Yeah. That's the number of oxygen. So I mean it's 37 halves, but that's the fraction of it. Now you're gonna multiply it. You're gonna have. Yep. What? Sure. So okay. So it's easiest to pick an atom that's only on one. So carbon's only here, or hydrogen is here, hydrogen here, oxygen, hydrogen. I get carbon, 6 carbons here, and 6 carbons here, and 13 here, so this is 13 halves water, because there's 2 there, but you can't have a half, so you multiply by 2. So you get 12 and 13. So 2 there. Now, next problem is, so if you look at oxygens here, so here it's 12 times 2, you have 24 oxygens here, and you have 13 oxygens here, so there are 37 halves, because there's these here, that's 37, so it's 37 halves of 2. You can't have a half, so you multiply by 2 again.
All right, so answer is C. All right, and we don't know if we're gonna be here on Wednesday, so I gotta blast on through. But let me ask you a question. What do you think? Does your car run more on air, or does it run on fuel? What do you think? So here's everything you've seen here shouldn't be a surprise. So this is the combustion of octane. So C8H18, 8 carbons, that's octane. Plus oxygen makes carbon dioxide and water. Balanced out is this way: 2 octanes plus 25 oxygens makes 16 carbon dioxides and 18 waters. Now, octane is 144 grams per mole. Oxygen is 32 grams per mole. Carbon dioxide is 44 grams per mole. Water is 18 grams per mole. So 2 octanes is 228 grams. 25 O2s is 800 grams. So 228 grams of octane reacts with 800 grams of oxygen, and that is 1,028 grams of reactants, forms 44 times 16, 704 grams of CO2, 18 times 18, 324 grams of water, 1,028 grams of product. So 1,028 grams of reactants, 1,028 grams of products. There are however many, 16 atoms of carbon, 36 atoms of hydrogen, and 50 atoms of oxygen. They just change places, right? So everything you've learned here is done properly. And so what? Well, among other things, your car more runs off of air than it does fuel, but at least by mass, by about a factor of almost 4, right? So not a big deal for here on Earth, but what if we're running a rocket and then we have to care about the amount of oxygen? Like, what do we do about that? Where there's no oxygen in space, it means we have to carry oxygen with us. You can see oxygen's pretty heavy. So that's a problem. So, and there are some rockets that run off of fuel. Well, hydrocarbon fuel. The Saturn V rocket that went to the moon, that ran off of kerosene. So the other thing is if you, we don't do this, there's not talk about this anymore, but there was some talk about having carbon credits. So, and specifically, you could, it's per ton, it's to be $30 carbon credit tax on carbon dioxide, so $30 per ton of CO2. And I remember when there was talk about this, I was a consultant for a billionaire by the name of Robert Addington. He did a bunch of coal, especially in Kentucky. And he loved the idea of carbon credits. He thought it was the best thing. He was hoping that it would happen. And this is what he liked about it. So if you had 1 million acres, you had 1 million acres of land, and from that you can get $1 billion worth of coal out of it. So in Kentucky and most of Appalachia, the common method of coal extraction it's known as strip mining. You just rip off the top layers, and then you get coal seams, and you grab the coal. And what they had to do for that, I mean, you can't just leave 1 million acres of bare land. Well, I guess you could in the past. Plant trees. And the trees, so you get the trees would, there's a bunch of research has been done for carbon dioxide sequestration, and trees have been said to have its 20 tons CO2 per acre per year. So that means that 1 million acres will have 20 million tons CO2 per year, and then it's $30 per ton, so we're at $600 million for the carbon credits, and in like 2 years, the carbon credits are worth more than the coal. So if you have the mineral rights to some land and you strip mine it and then you plant trees, that's a lot of money coming your way in carbon credits. So he's like, that's a great idea. So let's do it. But we haven't done that yet, so it doesn't look like it's going to happen anytime in the near future. Carbon credits, at least. But when there was talk about this, there was a bunch of research being done for what kind of crops can sequester carbon. And there was some issues with this because there was an international cooperation in this, and the United States just kind of kicked everyone's butt when it came to our crops. So like in the United States of America, the Mississippi River Valley is just like, especially the Ohio River Valley, is just the best cropland in the world. No one could come close to us. And the reason for that is because of Canada. Because every 100,000 years or so, we have this 100,000 years thereabouts of ice age and about 10,000 years of interglacial. So we're in an interglacial right now called the Holocene. So, and our interglacial has been kind of long. It's been the order of about 15,000 years. So we're due for another ice age. Just by average, by the laws of average, doesn't mean it's going to happen tomorrow. But so what happens is every ice age, all the topsoil gets scraped off of Canada and plopped right down to where Ohio, Indiana, Illinois, and Iowa are. And then 100,000 years later is another big plop of Canadian topsoil. So, and the other thing that we do in the United States is we put lots and lots of fertilizer on our crops. with specially nitrogen fertilizers. We just throw bunches of it on there. And because of those two things, probably most of the topsoil though, we have the best, most productive cropland in the world. And so like Ireland was looking at the crop yields in the United States, they're like, yeah, we can't compete with you. There's no way we can't. And so I mean with regulations having like, okay, well, if I grow my corn and then I plow my corn back into the ground and not harvest any of the biomass, can I sell my carbon credits? And the answer would be yes. And how many carbon credits can I do though? And that was kind of what they were arguing there. Where the other place they were looking at for carbon credits was with algae. And what's nice about algae, also looking at it as a biofuel. So what we use typically for biofuel in the United States, and we use this here in Hawaii, is ethanol from corn. So corn ethanol. And so if you look at corn, so corn, when you plant the seed, it has to grow roots, it has to grow a stalk, grow leaves, and then has the fruit. Harvest the fruit, get the sugar from the fruit, and turn it into ethanol. Algae is single-celled. Divide, 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 divide. No roots, no stalks, no leaves, just product. So, and you can tweak algae to produce sugar, to produce lots of oils or protein. The other use that we're looking for algae is a food source for space colonists. So if we go to Mars and we go colonize Mars, we're probably not going to be eating taro. We're probably not going to be eating corn. We'd be eating algae. So that's that would be the primary staple of our diet if for humans that are colonizing other non-terrestrial, like non-Earth locations. At least from what we know now, algae would be a big part of it. So if you like, you guys ever seen the movie The Martian or read the book? The book is awesome. The book is better than the movie if you have a chance. Anthony Weir, I think his name is. Weir is his last name. Anyways, he wrote a book called Artemis. It was about a moon colony, and the people there ate something they called a gunk. It was algae, basically. So I like The Martian better, but the Artemis is still a good book if you want to read it. And the Martian, it's pretty funny. Get a chance to read that. But anyways, so, and it's scientifically accurate. At least the chemistry is. So, okay, so back to biocrops. So some other things, the algae, and where I'm building up to is a concept called the linear reagent. And algae is a good one to talk about because algae grows until it is limited by some sort of nutrient. And in the Mississippi River Valley, the nutrient that it's missing is phosphorus. So maybe you've noticed that the formulations for some certain things have changed. The dishwashing liquid used to have phosphorus in it, now just has carbonates in it. But they stopped putting phosphates in dishwasher liquid. They used to put it in laundry detergent too, but you can't do that anymore. The reason for that is in anywhere in the Mississippi River Valley, right? But so Colorado on east, if you put like the waterways started becoming clogged with algae because the phosphorus from the detergents would go in the waterways and you get an algal bloom, and all the other plant and marine, and well, not marine, it was freshwater, whatever, the fish life would all die. And that's a specific type of pollution called eutrophication. When nutrients are added to the environment, you can sometimes get, it depends on the nutrient, depends on the location, get algal blooms. Also, in the Gulf of Mexico, there are algal blooms seasonally from farm runoff because of the nitrogen fertilizers that are put into the crops. The nitrogen comes down the Gulf of Mexico, and there's a huge algal bloom. And that sometimes can be bad because it can sometimes get red algae, and that's toxic. Now, eutrophication is not always a bad thing. It happens naturally. So, for instance, well, the other thing, many people don't realize this, but the oxygen in the air doesn't come from, well, plant life like trees or grass. It does, but the majority of the oxygen in the earth, so 75 to 80% of the oxygen in the earth comes from algae. So if we were, let's say an alien, sort of like extraterrestrial alien came to categorize the Earth, they would say, well, the Earth is a planet that's mostly made of iron, that has a silicate crust on the surface. The surface is about 2/3 water, and the dominant species are single-celled algae. So, but then there's these bipeds that think they run the show. Algae is the dominant species of sorts on the planet. It's where we get our oxygen from. And it's altered the atmosphere. It's without algae, there would be no Earth. Well, at least Earth as we know it, I should say. And it can be useful. We're looking to use it as a crop. So talk about space exploration, looking at it for biofuels. The problem with it is cost, capital investment. So you can do what's called the open pond method. Basically, dig like a shallow swimming pool, just put concrete down, or like a thick plastic tarp down, and dig a hole and put in water and nutrients, and algae grows. And the problem is that a lot of water evaporates that way. So you can put a plastic sheet over it, but that costs more money. The other problem with algae is that every 2 weeks or so, the whole colony dies. And it is believed to be because some outside algae gets in and kills it all. So the first few days, after the first days of seeding an algae pond, it does great. Then 2 weeks later, it's gone. It makes it hard to do. It's very cost intensive to have an algal farm. There's also talk now about, I mentioned the two-dimensional pond. There's thoughts of making things 3D. So maybe farming in the future, especially as the planet gets more and more cities in it, that we can start planting trees and whatnot, or strawberries like up the sides of buildings, and maybe even have, there's a company called Vertigrow. They basically take like a shower curtain, and they have water that kind of goes back and forth, and you can grow algae that way with nutrients. Maybe there'll be hydroponics, and you'll be growing, like I mentioned, strawberries, or something that's easy to grow. Lettuce or something like that you can have in little pockets and fluids, water's coming by, like a hydroponic kind of thing. That might be the future. I don't know. That's what some people think. If you're wondering, there are think tanks that think about, what's the future of food going to be like? Many of them think it's going to be 3D printed. So you can go to Kirkland and buy your insect-free protein packet and vitamin C packet and whatnot, and put it in your 3D printer, and then print out something that's like chicken nuggets or something like that, and eat it. Who knows? That might be the future of food. I don't know. But okay, so back to algae. We've talked about the interests of biofuels. It's important naturally. So I told you by location. Around Alaska, the limiting nutrient for algae there is sulfur. And the ocean around Alaska is very shallow. And with a seasonal change, the bottom of the ocean gets stirred, and sulfur comes to the surface. And then there's a huge algal bloom there. And it's also important for us here in Hawaii because the algae promote krill to feed off the algae, and then humpback whales come from Hawaii. They go up to Alaska, eat all the krill. They come back down to Hawaii, and then they mate and give birth, and then they go back, they get hungry, and they go back up north, and then they eat all the krill, kind of thing. So they go through this cycle of starvation and just immense gorging. Algae then, you can see algae goes by some sort of limiting nutrients, and algae works that way pretty well because it's single-celled. I mean, the more complicated plants, they have different things, and the same thing also doesn't work for humans because some nutrients we can make ourselves, some we can't, and we can also get more out of our food if we need to, and we can burn other things. We don't have to run off of sugar. We can run off of fats and proteins, for instance. I mean, if we have a limited sugar diet, we can change the way we do our food or the way we operate. So algae is a little easier, but the same thing is also similar to algae. Same thing is true for chemical reactions. So chemical reactions will go, if given enough time, they will go until a reactant runs out. So driving your car is actually a limiting limiting reactant problem, but it's the fuel. You don't drive your car and you're like, I wonder if the atmosphere is going to run out of oxygen. Like, no, the atmosphere is not going to run out of oxygen driving your car around. In space, that would be an issue because you have to bring your own oxygen. But driving a car, it's the fuel. Fuel is the limiting factor. So let me illustrate this. Let's go back to childhood, and we're going to make a Happy Meal. So what's in a Happy Meal? Toy. Anything else? Burger. Burger, fries. Anything else? Isn't there a drink? Apples. It's been a while since I've had a Happy Meal.
Some sort of like dessert.
Okay. I'll do apples. This is a healthy chemistry class. Okay, if we have 1,000 toys, 1,000 burgers, 10 fries, 1,000 drinks, and 10,000 apples, we're very healthy here. How many Happy Meals can we make? 10. Why only 10? We got 10,000 apples sitting there, right? You're limited. There is something limiting the reaction going, limiting the product. And what if I tell my manager, like, I can only make 10 Happy Meals? Like, fine. Here's 1,000,000 toys. Go make me 1,000,000 Happy Meals. And like, nope, still only 10. I'm just gonna have lots and lots of toys left over, right? Because if you need to make more, got to determine what the limiting factor is. So this is easy. It's all 1 to 1 to 1. How about the good old ham sandwich chemical reaction? 2 pieces of bread plus 1 slice of ham makes a ham sandwich. So if I have 1,000 pieces of bread and 1,000 pieces of ham, how many ham sandwiches can I make? 500, right? And then plus I will have 500 hams left over. So I'll have excess ham. So if I wanted to make more ham sandwiches, I need more bread. And this one's a little bit more complicated because of this 2 to 1 ratio by the balanced chemical equation. So keep that in mind. Okay. So stoichiometry, photosynthesis, plants convert carbon dioxide and water into glucose. And suppose a plant consumes 37.8 grams of carbon dioxide in 1 week with an excess of water. How much glucose in grams can the plant synthesize from the carbon dioxide? Now, more likely than not, the CO2 wouldn't be the one that was measured. It would be more likely would be the glucose at the end, is what you would look at, because it's really hard to measure the CO2. Let's go ahead and do this one. So this is a limiting reagent problem, and just like your car's limiting reagent is a fuel. You're told we have a limited amount of one, and then the other is in excess. So let's do this one here, 37.8 grams of CO2. And then, so dimensional analysis, we go, hopefully you're starting to think moles CO2 to 44 grams CO2. And here's the next step that's going to be the new one. We have a mole of glucose, C6H12O6, to mole CO2, 6 moles CO2. And I'm getting that from here, the 6 parts CO2 to 1 part glucose. So this is it's important to have the proper balanced chemical equation. If the chemical equation is not balanced properly, then the ratios will be wrong. So proper balance there is important. The last step is 180 grams of glucose per mole of glucose. I just had that memorized. I have 44 grams CO2 and 180 grams glucose memorized, 18 for water, that kind of stuff. And you put this in your calculator, and what do you get? 37.8 divided by 44 divided by 6 times 180. I get 25.8 grams glucose. GLU is short for glucose. And don't mind the other ones there if you're looking at it later. All right, so recap with this one. We have a limiting reagent problem. This is in fact, a limiting reagent problem, and we have an excess of 1, so we don't really have to worry about where the other stuff is. So, I mean, you don't have to worry about the water, I should say. It outright says that carbon dioxide is limiting reagent because there's excess water. And so we know what our limiting factor is, and then we set up a dimensional analysis, and the new step is this ratio between carbon dioxide, the reactants, and the products. And it's important that the chemical equation is balanced so that way it gets the proper ratios and therefore the proper numbers. And then we get about 26 grams from that 38 grams of carbon dioxide. So, questions with this? Okay. And so let's look at this conceptual connection here. And we have, look at this flask. We have nitrogen plus 3 hydrogens makes 2 ammonias. And this is interesting, among other things, because this is one reaction the book actually gets correct. This is, in fact, how we make ammonia. So we make ammonia this way, and ammonia is very important. It would change human civilization if we didn't make it. I can talk about that in a little bit. But let's look at this. It's reacting, and the number of hydrogens that we have, I'll note them in pink. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 hydrogens, and then we have 2 nitrogens. So from this, though, if this reacts all the way, so the limiting reagent here is actually nitrogen. So if well, first of all, 8 doesn't have the nice round number, but the 2 nitrogens, this will then make it'll make 4 ammonias. I should make the pen smaller. This will make 4 ammonias, but then that will only get 4 H2s with that. No, actually, no, I'm sorry, it'll be 6. 4. That will use 12 hydrogens or 6 H2s, and then we'll have 2 H2s left over. So does that make sense? With all this, we have an excess of hydrogen. So here we'd have to pay a little more close attention because that's pretty close. That's a pretty close value, or at least it's not like the other ones you say, oh, there's so much of the other, you don't have to worry about it. So which image reflects that? So this image here, A, this is not yet completed reacting. So there's still the nitrogen reactant here. The B is how much ammonia we'd have, but we still have leftover hydrogen. Leftover hydrogen is right there. So C is the proper image of that. So the next thing we're going to do is we're going to talk about doing that but using numbers. Before I get in there, let me talk a little bit about chemistry and society. So this equation here, nitrogen plus 3 hydrogens making 2 ammonias, this is very important because of human population and warfare. So if you look at the population of the human race, it basically kind of went like this really slowly. Then about the year 1900, it went like this. So 2 things happened in the year 1900, or in around the year 1900. The first one is ammonia synthesis. So we were facing around the year 1900, our population was about 2 billion. Right now it's about, I think that's like 7 or 8 billion. I don't know, or is it 9 billion? I don't know. 7.5? I don't even, we shouldn't argue. We have Google. Google. Come on, Google. What is the population of the Earth? Anytime, Google. 7.6? All right, you beat me to it. So 7.6 billion. So we went from 2 billion and like raising, doubling the population in like 1,000 years or something like that, I don't know, to doubling almost twice in a little over 100. So why did the population have such a huge boom? First is ammonia synthesis, specifically food production. So near the end of the beginning of the 20th century, end of the 19th century, I'm sorry, the end of the 19th century, beginning of the 20th century, we were facing what's known as a Malthusian catastrophe. That is the idea that the population has outgrown its ability to feed itself. So that's known as a Malthusian. You can apply it to other things too. Like it's just when your resources run out versus population growth. Because population growth grows exponentially, and then production of things tends to go linearly. So if you want to have twice as much product, you build twice as many factories. If you want twice as much food, you plant twice as much crops. But what do you do if your population grows exponentially? You'll run out of the ability to supply people with the things they need. So, and plants, they require large amounts of potassium, phosphorus, and nitrogen. So we as humans, our macronutrients are carbs, fats, and proteins. Right? We need lots and lots of those. We have micronutrients too. Right? We have vitamins and minerals. Those are our micronutrients. Plants have macronutrients, and they have micronutrients too. Of course, similar to plants, plants require lots of water and carbon dioxide, like we need lots of water and oxygen. I mean, if you look at what we really consume the most of, it's going to be oxygen and water. I mean, it'll be oxygen by mass. But anyways, we also need food, and plants need food too. Plant food is potassium, nitrogen, and phosphorus. Potassium and phosphorus we mine. Nitrogen we used to mine, but we need a lot of nitrogen, and the mines were running dry. So, and we used to mine it in South America. So that's where we're getting all the nitrates. And as a matter of fact, also organic food. So if you buy organics, there's no synthetic fertilizers. You can put mined fertilizers on organic food, so that's allowed, but not synthetic nitrogen. So, but then this is a big problem. Lots of money was invested into it. Germany figured out how to do it, specifically Karl Bosch at the BASF. It's a big chemical company in Germany, BASF. He figured out that if you got iron ore from Sweden and you heat it up in the presence of hydrogen for about 8 hours, it made a good catalyst. I don't know how the heck he figured that out, but he figured it out. In the United States, well, we actually used Niagara Falls. We used the hydroelectric plant in Niagara Falls, and we were making cyanide. So another way you can make nitrogen fertilizer is you can buy lightning bolts. Lightning bolts will fixate nitrogen, and so we were doing electronic discharge and making cyanides and putting cyanides on crops. But that went to, we don't do that anymore. The other way you can put nitrogen in crops, there's a series of algae called cyanobacteria, and cyanide is CN. So cyanobacteria makes cyanide-like compounds from air and carbon dioxide, essentially. So cyanobacteria is a nitrogen fixating molecules, and they can live in the roots of things like clover, and I think soybeans are too. I'm not entirely sure. They are nitrogen fixers. So it's not the plants, it's the symbiotic cyanobacteria with the plants, specifically in the roots of the plants, that do that. But the nitrogen fertilizer, it's the crops are on steroids. The production, the food production now is just immense. So it's ridiculous. If you compare it to like organic farming or even like pre-industrial age farming, we get so much food out of our cropland because we mass produce it. We industrialized it. So we have machines pick it. We don't have humans picking it. We are putting fertilizers, pesticides. If there is a swarm of locusts coming to eat all our crops, what do? We spray the locusts with nerve gas and they all die, and our crops are saved. So we don't have some of the issues that we had in the past with insects eating all our crops and whatnot. So we got lots of food, too much food probably, right? So we get all our corn and all of our, so that way we can go to Krispy Kreme and eat all the donuts we want, right? We don't have to worry about it. We're not going to starve people out. So so anybody want to guess what the other thing? So I said that nitrogen fixation, specifically ammonia synthesis, that's one of the reasons why we had a huge population boom. Anyone guess what the second reason is? Medicine. Do you know a specific type? Not polio, but not vaccines. Penicillin. Yeah, well, antibiotics. So polio wasn't killing too many people, but it wasn't a death sentence. My grandmother got polio and she didn't die, and she wasn't in an iron lung at all. So I mean, it was just kind of, a large number of people were, but I mean, it wasn't a death sentence. I mean, even Ebola, like a lot of people survived Ebola, but still, I'd hate to get the Ebola virus. But bacteria is nasty. Whew. Like if you look at what killed people back 100 years ago, what's that? Yeah, well, yeah, disease though from that, right? I mean, but yeah, I guess sanitation. But there were ways around that. Like the Middle Ages, they had really bad sanitation, but they got around that by drinking lots of beer. Because they would, yeah, at least I'm recording this on YouTube, the night soil, they used the human feces to use their crops, right? So there was lots and lots of human and animal waste being put back into the environment. But yeah, sanitation, of course. And now we can purify our water by chlorination. So back in the Middle Ages, they just made a lot of beer. And they did it, well, they sterilized by heating it up. And the beer, if you also wonder, the beer back then was not as concentrated as the beer now. It's only like 0.5%-ish, so alcohol. So it's not like, I mean, here the beer, you're drinking a pale ale, or sometimes they're like 9% or something like that, or 6% or higher. I mean, if you drink that all day, you'll be drunk all day. But if you drink a non-alcoholic beer, you should, unless you have a dehydrogenase enzyme issue, you'll be fine. Anyways, yeah, so antibiotics, because before that, like sanitation, but I mean the things people died from, septicemia, so I guess that could be from sanitation, pneumonia, was a big thing. So I mean, people still die of pneumonia, but it tends not to be people in their 20s and or 30s, right? So disease rarely kills people of our age. So for people our age, if we were to die, it's usually accident, murder, or suicide. That's kind of the top killers. And does anybody know what the top killers are today? Heart disease, yeah, cardiovascular, heart disease, stroke, one more. What? Obesity? I guess you could argue that. That usually leads to cardio problems and cancer. So slow disease. So slow disease gets us in old. That doesn't mean that you or I, I guess everyone looks like in their 20s. I'm the old guy here, in my 30s. We tend not to die from cancer and or heart attack or stroke. But that's what gets most people. I mean, you could argue to obesity because that also leads to cardiovascular disease. It could also lead to kidney disease too, so it doesn't necessarily have to be that. You can do a lot of things with that. Okay, so old people disease, what gets us now? So that means there's more of the population at the reproductive age that survive. So that means you get more children survive. And there's enough food to feed everybody. So what happens to population? Climbs exponentially. So, and I also said there's an issue with warfare with this. So ammonia synthesis happened in Germany. And what did Germany do after they figured out ammonia? Like, yes, we can feed the planet now. But what do they also know that if you burn ammonia, you can make nitrogen oxides. And you can react nitrogen oxides with water to form nitric acid. And if you take glycerin, the glycerin molecule, you can get that from any fat. So take glycerin from fat and react it with nitric acid, you get nitroglycerin. So that is also what's in dynamite. Does anybody know what TNT stands for? It stands for trinitrotoluene. So how do you think you get that? Yeah, 3 nitric acids to 1 toluene molecule. Toluene is just benzene with a methyl group on it. So, which means also nitric acid, if you mix it with things, they tend to make explosives. And I believe the reason why you can't carry liquids on planes anymore is because if you mix nitric acid and glycerin together, nitroglycerin are shock sensitive. So if you took a bottle of that and if you threw it, or hit the side of a plane or threw it on the floor, it would explode. So you can make shock-sensitive stuff with that. But there was a guy named Alfred Nobel. He figured out that his family, they had a nitroglycerin factory. It blew up and it killed his brother. And he wasn't happy about that, so he said, I need to make this stuff safer. So he figured out if you mixed it with diatomaceous earth with clay, so nitroglycerin with clay makes dynamite, and you just have to put something on there that'll kickstart the reaction, a blasting cap, something like a magnesium charge, or something like an azide can be used, like a mercury or sodium azide. That'll make the whole thing explode. So you have a very safe explosive now, which could be used to blow up mountains to put trains through, but instead it was frequently used to make bombs. And so what people started calling Nobel was the Doctor of Death. He was a Doctor of Death, and he felt kind of bad about this. He was making lots of money, but he was known as the Doctor of Death. And so he hired some people to think like, okay, how can I not be known as the Doctor of Death? And he says, all right, they said, put aside a bunch of money and make an endowment that when you die, that there will be a panel of people that will figure out someone who has done something to promote peace in the planet and give that person a prize, and then people will think of your name Nobel. They will associate it with peace and not with death. So that's how we got the Nobel Peace Prize, was from the guilt of Nobel. It's actually 6 Nobel Prizes. Nobel was really big into science, so there's a Nobel Prize for chemistry, physics, physiology, which is medicine. Then economics is another one. The last one is literature. Apparently Nobel, he liked to write, but he apparently was terrible at it. So his family tried to hide all his publications. I don't know if you can still find them, but there is a Nobel Prize for that. And those 5 Nobel Prizes are offered through Sweden. So Nobel was Swedish. And so the King of Sweden presents the 5 non-peace prize. The Nobel Peace Prize is presented through Norway. So, and the reason for that is Norway were the peace-loving hippies of the 1920s in Europe. So like right now, I'd be like, oh, who are the peace-loving hippies in the United States? You'd probably think people probably think San Francisco, like Berkeley and Haight-Ashbury, like all the hippies. Or maybe think Kauai. There's a lot of hippies in Kauai too. So if there was a Hawaii Peace Prize, it would probably be offered from Kauai, right? So, but that's the same idea. So then the hippies of Europe at the time were the Norwegians. So the only one there that's put out for non-Swedish thing. So also with politics in World War II. So I mentioned that the iron for this reaction had to come from Sweden, and what it was aluminum and potassium impurities in the iron is what made it special. So we figured that out in the 1970s. So up into the 1970s, all the catalyst to make ammonia was mined in Sweden. Now we can get it anywhere. So it's actually gotten a lot cheaper. We tend not to make it in the United States even. Most of the ammonia is made in Russia, as a matter of fact. But the iron is needed for this reaction, and it's needed to make ammonia for explosives and for fertilizers. And Hitler needed the iron, and he struck a deal with Sweden. If you know your history, Sweden was neutral in World War II. And it required them, though, Hitler made them pay a tribute of the iron. So, because Hitler thought, okay, I need the iron to run my war machine, but if I attack Sweden, I might knock out their infrastructure to produce it, and it would slow me down. So he struck a deal instead, and so it let him go faster, I guess. So, but history and politics and chemistry can actually be very, very interconnected. And World War II would not have been able to, well, World War I and World War II could not have been fought with that. We haven't had any big wars since then because of nuclear weapons. So they're just, the casualties would be too high. We would get rid of our population problem, but there would be other, there'd be other problems, right, for a large world conflict. Okay, so this is probably a good place to stop. So hope you like a little bit of the chemistry and society stuff. But if not, I will see you then. I don't know about Wednesday. Keep your eyes peeled to your emails for that. And it did